So again, hello everyone. In this second part of lecture 9, so we will be considering the Carnot cycle. So recall that in cyclic engines, if the engine is to operate continuously, it has to be restored to its original state so that it could expand again and produce work. So this can be achieved only if the working substance loses heat. So also, recall that in second law, it is impossible for a substance to undergo a cyclic process whose sole effects are the flow of heat into the system from a cold reservoir and the flow of an equal amount of heat into the hot reservoir. So thus 100% efficiency is impossible. So if we will be considering the principle of a basic heat engine, so the movement of piston causes the production of continuous work. Input of heat is required in order to increase the temperature of the working substance. So this is usually steam. So high temperature steam in, the steam is operating at higher temperature, at higher pressure. So therefore, do you have a net force that causes the piston to move from left to right, thus pushes the cooler gas outwards, and the hot gas cools down. Now, in reverse, the higher temperature steam in contrast with the cool gas, pushes the piston to the left, thus going back to its original state. So thus, continuous mechanical work is produced. Now, let us look at the way in which the most efficient engine is possible, which is a Carnot cycle. So what is a Carnot cycle? A Carnot cycle is a sequence of reversible, isothermal, and adiabatic processes wherein heat absorbed at high temperature TH is converted to mechanical work W, and the waste rejected at a lower temperature TC. So why is Carnot cycle the most efficient engine possible? Since all of the 4 steps or processes here are all reversible. So meaning we are doing the maximum work done by the gas and the minimum work done on the gas. So note that the working substance here will be assumed to be an ideal gas. However, it's also possible to use a non-ideal gas. So the Carnot principle states that no heat engine can be more efficient than a reversible heat engine when both engines work between the same temperature. Now, the Carnot cycle, as I mentioned earlier, so this is a cycle that most efficient engine is possible. So if we will be considering the graph, the PV diagram on the left, so the Carnot cycle consists of 4 steps. Number 1 is the isothermal expansion from point A to point B. The second step is the adiabatic expansion. So the gas expands, but it changes the temperature from TH to TC. Step 3 here is the isothermal gas compression from C to D. And lastly, adiabatic gas compression from D to A. So the Carnot cycle is the most efficient way in which we could do maximum work while minimizing heat input and heat output. The region here represents the work done by the gas minus work done on the gas. So the diagram on the right, so you're familiar, you saw this in the previous lecture. So if the system, heat in at TH, it produces work at W and loses heat at TC. Now, the processes involved in the Carnot cycle are the following. So number 1 is a reversible isothermal expansion at TH. So in here, the volume changes from A to B. So the second step is a reversible adiabatic gas expansion from volume VB to VC with a consequent lowering. So this time the temperature decreases from TH to TC. Now, step 3 is a reversible isothermal compression at TC from volume BC to BD. And the last step is a reversible adiabatic compression from BD to BA with a consequent increase of temperature from TC to TH as it goes back to original state. Now, so this is again the Carnot Cycle PV diagram and the Carnot Cycle ST diagram, but we will be discussing S or the entropy in the next lecture. So let us try to understand each step in the Carnot cycle. So again, going back with step 1, so this is a reversible isothermal gas expansion. So in this process, the amount of heat absorbed by the gas from the heat source at temperature TH, the gas expands and does work on the surroundings. So in this process, heat is absorbed from the high temperature reservoir to do work. Steam is being heated up by the hot reservoir, and at the same time, it expands, pushing the piston. Therefore, it does work. So since expansion is isothermal, the total change here in internal energy is 0. The heat done by the gas is equal to the work done. Now, in terms of equation, so recall that for reversible isothermal gas expansion, delta U is equal to 0, Q is equal to negative W. Reversible work is negative nRTH, L and VV over VA. Thus, Q is equal to positive nRTH, L and VV over VA. Step 2 is reversible adiabatic gas expansion. Here, the system is thermally insulated and the gas continues to expand and the work is done on the surroundings. In an adiabatic expansion, the gas expands adiabatically as it lowers the temperature from TH to TC. This time, the gas here is pushing the piston with no heat input. At this point, the gas is expanding against the piston, but this time, it's now cooling down and done adiabatically. So this is adiabatic gas expansion. Keep in mind, Q is equal to 0. Delta U is equal to W, which is equal to NCB TC minus TH. Step 3 is reversible isothermal gas compression. So in this process, the heat loss Q out occurs when the surroundings do the work at temperature TC. In this step, the heat leaves the system into the cold reservoir as the system compresses. In here, we are trying to bring back the gas, but at the same time, discarding some heat as our waste heat. So since expansion again is isothermal, total change in internal energy is 0, and the heat absorbed by the gas is equal to the work done. So in terms of equation, delta U is equal to 0, Q is equal to negative W, work reversible is negative NR, it's TC, Ln, the final volume here is VD over VC, thus Q is equal to positive nRTC, Ln VD over VC. So the last step, which brings back our system to its original state, is a reversible adiabatic gas compression. All of the work done on the system here is done on the system to increase its temperature to original state. So in an adiabatic compression, gas is compressed adiabatically from TC. It increases the temperature TH as it goes back to original state. So keep in mind, Q is equal to 0, delta U, or internal energy, is equal to work, equal to NCB TH minus TC. Now, let us summarize the steps. So, A to B, again, A to B is reversible isothermal gas expansion. Delta U is equal to 0. Work is equal to negative nRTH, L and VV over VA, and Q is equal to positive nRTH, L and VV over VA. B to C is reversible adiabatic gas expansion. Q is equal to 0, work, and delta U equal to NCB TC minus TH. So C to D is isothermal gas, reversible isothermal gas compression. Delta U is equal to 0. work reversible is equal to negative NRTC ln VD over VC. Q is equal to positive NRTC ln VD over VC. The last step is adiabatic gas compression. Q is equal to 0. Work is equal to delta U equal to NCB TH minus TC. So this term cancels out. So we know that since it's a cyclic process, change in internal energy is equal to 0. Q cycle is equal to this term. Work cycle is equal to this term. Now let us consider the relationship between V1 to V2, V3, and V4. Recall that in steps 2 to 4, so this is an adiabatic process, volume and temperatures are related through the following equations. Recall that for adiabatic process, T2 over T1 is equal to V1 over V2, but the exponent is gamma minus 1. So step 2, it's Tc over Th equal to Vb over Vc raised to gamma minus 1. The last step, step 4, Th over Tc is equal to Va over Vd raised to gamma minus 1. Now, the equivalent relationship is Vc over Vb equal to Vd over Va, or Vb over Va is equal to Vc over Vd. So for you to further understand their derivation, so this is their relationship for adiabatic process between temperature and volume. So step 2 and step 4. So to change this to Th over Tc, we get Vc over Vb. So since they have the same exponent gamma minus 1, this cancels out. So the relationship is Vc over Vb equal to Vd over Va. Simplifying the Q cycle and the work cycle here. So recall in the previous slides, Q cycle is equal to nRTH ln VB over VA plus nRTC ln VD over VC. But VD over VC is equal to VB over VA. So simplifying the terms, Q cycle is equal to nR the quantity TH minus TC, since they have the same ln VB over VA. So it's a common factor now. Thus, work cycle is equal to negative NR TH minus TC ln VB over VA. And if you add the two terms, delta U is equivalent to 0. Now, in summary, so you have an idea how Carnot cycle is coined as a term as the most efficient engine possible. And the efficiency of a heat engine cannot be higher than that of a reversible heat engine. So in the last part of lecture 9, we will be discussing the calculation of efficiency of heat engine as well as entropy.